Should we go ahead and start? All right,
Sure, sounds good.
cool. All right. Hi everyone. So, as mentioned last week, we're going to kind of finish the confidence intervals discussion. I couldn't be there in person due to kind of having a little bit of a cold going on right now, and I didn't want to get anybody sick. So, but yeah, so today we're going to talk about confidence intervals. And then Josh will go over a data example, like a case study. If you haven't signed in yet, please go to the sign in sheet and sign in. And then for the code, we're going to be using last week's code for the confidence intervals bit. So hopefully everyone has maybe started a DCC on demand profile and gotten this loaded. So first off, I'm going to kind of start a new session. And then I'm going to kind of rerun some of the stuff at the top of this sheet. So I'm going to do the code, the packages that we're using. Once it lets me go, I'm on it real quick, being a little. So all the packages. There we go. Okay, it's been a little slow today. And then the paths. And then I'm going to load the data. And then the one other thing is we're going to use this case 2 data, and we're going to, basically, we're going to be using this later on. So, okay. So now to confidence. Is everyone okay here so far?
Is the size good? Yeah. Okay.
So, okay. So I'm going to go down to confidence intervals. I'm going to switch over to the HTML sheet because that's a little cleaner, but we're going to go back and forth, kind of like what we did last week. So, what is a confidence interval? So, in kind of general, when we're talking about the confidence interval for some estimate like mu, which represents the population mean, um, it's kind of an additional information that we can provide. So, if we have a population that comes from a normal with mean mu and variance sigma square, we're interested in estimating that population mean. And if we draw some sample y1 through yn, then y bar is the best point estimator for mu, right? However, because this is a random variable, it's not going to, it's unlikely that y bar is going to be exactly equal mu, right? So with that point estimate alone, there's no real sense of how far away from the true population mean your estimate is. So what people like to do is give kind of an interval of ranges rather than say a single number. So kind of an example of what I'm talking about. So if we have a point estimate, that is say a meteorologist estimate that it'll rain at 3 p.m. Well, an interval estimate will be that a meteorologist estimates that it'll rain at 3 p.m., but it's possible that it'll rain anywhere from 1 to 5 p.m. Does that make sense? Or okay. So how do we construct? I'm going to turn on how do we construct a confidence interval then? So for kind of normally distributed data, if we have a random sample y1 through yn that comes from some normal, but we don't know the mean and we don't know the variance, the confidence interval for our mean estimate is going to be y bar plus or minus this critical value, which I'll talk about, the standard error, the standard deviation, divided by the square root of n. And that'll give us kind of our interval estimate of the population mean. So y bar here is the sample mean, s is the standard deviation, N is the sample size, and this T is the quantile of the T distribution with degrees N minus 1 degrees of freedom. So a T distribution is very related to a normal. So it's basically, it has one parameter, the degrees of freedom. It can range anywhere from negative infinity to infinity. It is related to a normal distribution. It is basically the ratio of a normal and a chi-squared, square root of chi-squared, and it has various functions in R. It was actually invented by someone who worked at the Guinness factory in Dublin. So we can go into R and you kind of see what this looks like. So I'm going to go down to this code right here, ZZ, and we're going to basically plot all these different, we're going to plot D norm, and then we're going to also plot DT with different degrees of freedom. So the first one will be the norm, and then we'll have the T distribution with 1 degrees of freedom and the T distribution with 10 degrees of freedom. Let me run this. So what we see here is, so the black line is the normal. The blue line is the T distribution with 1 degrees of freedom, and the red line is the T distribution with 10 degrees of freedom. So basically, the T distribution has a little bit more of a kind of wider at some of the tails, but with increasing degrees of freedom, it basically kind of converges to a normal. Any questions on that? Okay. So let's now kind of calculate the confidence interval. So we're going to calculate the 90th percentile, 90th, 95th, and 99% confidence interval for age in the case one study. All right. So I'm going to go into R. I'm going to say, all right, I'm going to let YY be basically case one age. All right. So we now have this big vector, 2000 long, 2500 long. We're going to take the mean. I'm going to call it YB. That tells us the mean age is 31.39. I'm going to calculate the standard deviation. And I'm going to calculate the length. So that kind of gives us the information related to the standard deviation and the sample mean. All right. So to calculate the confidence interval, we have this formula y bar plus or minus this critical value s divided by square root of n. And so we'll calculate that in R. Okay, so let's go back here. So the code, let me find the code here. So we're going to do it for the 90%, and then we'll do it again for the 95th. So what we have to do is we take the critical value. So it's 1 minus it's 1 minus 0.9 divided by 2. So take the critical value. It's going to give us 1.64. Take the critical value, and then we do YB plus the critical value times that standard deviation we calculated divided by the square root of n. And that gives us a 90% confidence interval of 31.09927 to 31.69. And we'll talk about how to interpret these next. So to calculate a 95% confidence interval, what we have to do is first calculate the critical value for 95%. So remember, it's 1 minus alpha divided by 2. So we calculate that. And then we calculate it again. So we get 31.04 to 31.74. So you can see it's getting a little wider. And then next up, we'll do the 99th. just type it in here. This crit, and we'll get 30.93 to 31.86. And if we wanted to calculate this using kind of base functions within R, we can use this t-test function. So we go t-test, x equals yy. We'll go confidence level equals 0.90. And if we calculate this, and we'll talk, it'll give us kind of the 90% confidence interval for this. And ignore the testing stuff, we'll get to that later, but this will give us that value. So you can see the confidence interval here, 31.09927 to 31.69226, which is what we had up here. And if we'd did for 0.99, we get that 30.93127 to 31.86026 that we got up here. All right. Any questions about that? All right. So for the interest of time, I'm going to skip this case 2, which was basically asking you to repeat this, but using the viral HIV RNA in that study. I'll fill this in and upload it, but for now, we're not going to do it. Okay. So how do we interpret a confidence interval? And this is something that's kind of tricky and something we need to kind of discuss. So this interval is kind of being constructed around some mean from a sample. So this interval is going to change every time we do a sample because the estimated mean will change every time we do this, right? So the interval may contain the true population mean mu, but sometimes it won't. So if we draw many samples and computed y bar and constructed a confidence interval, about 100 times 1 minus alpha of the intervals will contain mu. So alpha here I'm referring to as kind of the type 1 error. So in, say, our example test, we use 0.05. So that's when we say like 95% confidence interval. That's kind of what we're referring to here. So there's a couple different interpretations. The probabilistic, like really hardcore statistical interpretation, it says, in repeating samples from a normally distributed population, 95% of all intervals of this form will, in the long run, include the population mean mu. Or another interpretation is when we're sampling from a normally distributed population, we are 95% confident that this interval contains the population mean. And this is kind of the very common interpretation. It is not a probabilistic statement about the population mean. The true mean is a fixed value. It is not a random variable unless you're in like the Bayesian world, which we're not in this class. So the interpretation is wrong if you say there's a 95% chance that the true population mean is between some values. That's an incorrect interpretation. Because the probability it's within that is 0 or 1. It's either in it or it's not. The process of repeating the sampling over and over again gives us that kind of 95% confidence. So we're going to do a sample, an example of this via a kind of resampling over and over and over again and see what we get. Any questions about this? I apologize for my voice that I've been dealing with a cold. Okay. So we're going to generate a large normal data set, all right, with mean 320 and standard deviation of 240. All right. I'm going to go down here. Okay. So we have our data set. I'm going to set the seed. I'm going to generate this population. So it's a random normal, 50,000, mean 320, standard deviation 240. I'm then going to sample from it 80 times. And each time I'm going to sample 110 of them. All right. So this replicate function, what it's doing is it says replicate how many times you want to replicate. I say 80. And then what do you want me to replicate? I say, I want you to replicate sampling from this much larger vector about 110 observations each time. So what this is going to give us is this 110 by 80 matrix where each column is a sample from this data set. All right. So this right now is just going to construct a confidence interval for each of those samples. So it's going to apply over the columns and construct that confidence interval. So you can see you calculate the mean, we calculate the standard deviation, we calculate n, we calculate the critical value, and then we calculate the confidence intervals. So I'm going to define this function. So to give you an idea, if I do confidence interval, SAMPS column 1, it says the lower limit is 297, the mean estimate was 340.85, and the upper was 384.0113. All right. So we're going to apply this. So now we're going to have a 3 by 80 matrix where each column is a sample. The first row is the lower limit of the confidence interval. The second element, the second row is the mean, sample mean, and the third is the upper limit. And now we're going to plot this. So what we're going to do is basically plot this where we're going to have each kind of like indice kind of being an example sample. It'll make sense once I make this. So, all right. So what we have here is each little line is a confidence interval, right? And what we can see is blue is basically if it's covered, or teal, I guess it's a greenish teal. It means that it covers the true. So you see the red line is the mean, the true mean. And then the red means it does not. So if we counted how many of these 80 confidence intervals are actually covered, so let me see, 1, 2, 3, 4, 5, 6, 7, like 7 do not, right? 1, 2, 3, 4, 5, 6, 7. So meaning we had like a coverage probability of about 91. So if we keep repeating this over and over again, eventually it's going to reach 95%. So each time we construct a confidence interval, we're going to get or we do a sample and we construct a confidence interval, we're going to get a potentially slightly different range. But the idea is over time, that range, right, is going to cover the true mean. Does this make sense to everybody? Any questions about this? No? All right. So next up, let's talk about if it comes from a non-normal distribution. So we have y1 through yn, which is not from a normal, and it has some unknown mean and variance. So if you remember last week, we talked about the central limit theorem. Basically, and there's another theorem called Slutsky's theorem, that if, right, n is sufficiently large, we can construct an approximate confidence interval for the mean, where it's basically y bar, instead of t, we have the z 1 minus alpha over 2, standard deviation divided by square root of n. Okay, so basically, even when the data isn't normal, we can still construct a confidence interval if the n is sufficiently large. Okay, so we're going to do this for the cannabis data in case 1. So I'm going to go back here. and construct this. So I'm going to take this case one, and the variable is called marijuana. See, it's a bunch of zeros and ones. I'm going to take this. Basically, this actually isn't necessary, but we have it anyway. So we have YY, and if we do a table of that, it says there's 1,399 people who marked that they do not use cannabis. And then there's 1,105 that say that yes, they do. And we have 202,504 individuals in total, right? So we know this is probably a Bernoulli, right? Because a binomial with n equals 1, because it's a simple yes, no. So the population mean is just going to be like the sum of those is just going to be 1,105 divided by 2,504, right? That's our best estimate. So we can construct that, and that gives us 44. All right. So if the sample size is sufficiently large, we can construct this kind of 95% confidence interval. So it's going to be 0.44, basically, plus or minus z 0.975. So that's 1 minus 0.05 divided by 2. Another way to think about it, if it helps, is you can also get that if you go 1 plus 0.95 divided by 2 will also kind of give you that value if it helps in thinking it in terms of the confidence interval as opposed to the alpha. And then this square root p hat times 1 minus p hat, remember, which is the estimate of the variance divided by the square root n. So if we calculate that, we get 0.422 to 0.461. So this means is that we are 95% confident that the true sample proportion of individuals who use cannabis lies between 42.2% and 46.1% in this population. All right. Now, in R, there's not an easy way to get this confidence interval using kind of base functions like there was for that t-test that I showed. So if we go into here, basic, so there's this prop.test where you pass, you give it the sum of how many successes you have, you give it the n, and you put this correction equals false. So this is basically something, there's some theory around called Yates correction, which we don't want to get into, but with proportions. So this will give a confidence interval of 0.42195 to 0.4608177, which you can see is not exactly what we got when we constructed it this way. And what this is it's something called a Wilson confidence interval. So one of the things in statistics, right, is and just in general, right, people love naming things, is everything has to have a name. So this was a confidence interval for proportions derived in like the 1930s by a guy named Wilson. And this is kind of what's been used in here within this prop.test. And it's basically this kind of convoluted formula, and it's supposed to have a little bit better coverage for kind of small samples. But in base R, there's no exact way to get this confidence interval that we constructed, which is generally referred to as a walled confidence interval, WALD. Yeah, so do people want to do this example question, or should we kind of keep going? I'd say silence is keep going then. So just as an example, we're going to talk about this. We're going to look at cocaine use within this data set. So I'm going to set dot seed, right? And I'm going to pool, just randomly sample 100 individuals. So I take this data set, I sample this slice underscore sample says like sample from the rows 100 and then pull the variable cocaine use, right? So now we have this cocaine use variable within our data set. And we can get the mean value. So the mean value is 0.03. That's our estimated uh, proportion of individuals who use cocaine within this population. If we construct the confidence interval as before, we get a negative 0.003 to 0.06, right? So one of the things that can happen with when you're dealing with non-normal data and constructing these kind of confidence intervals is you can get values that are outside of the range of possibilities, right? You can't actually have a negative proportion. So this is just something to think about. And there's methods out there that say maybe use the fact that the data is from a binomial or a Bernoulli and is actually 0 and 1s to construct a confidence interval that maybe better suits the data. This is just kind of an aside, but just kind of wanted to mention. So summarize, when the data is normal, we have this confidence interval here, y bar plus this t distribution. And when it's not normal, we have this kind of approximation using the standard normal. Any questions? I think that was it. I kind of blazed through it. No questions in the room?
No.
All right. Great. Well, I'll go ahead and turn it over to Josh then.
Actually, let me put on the.
And we'll have like a little tech thing as he. Oh, no, that was seamless. Look at that.
That's, I don't get any credit for that. That's all Matthew.
Yeah. Big shout out to Matt.
Yeah. Definitely. Okay. So, what am I doing here? So I'm shifting gears, and like Richard said, I assume people on Zoom can hear me okay? Is it too loud in here? I feel like it's a little echoey. Let's see, that's number 1. How about that? Okay, can people on Zoom still hear me? Oh, good. I got a thumbs up. Okay. And Richard, you did the sign-in thing, right? I'm not just imagining that. Okay, so, and is my RStudio good size? You want the font bigger? Anyone on Zoom want the font bigger? Okay, so I'm going to be working from, whoops, I probably should put it there. Let me see if I can. Now I lost it. Uh-oh, that was weird. I don't know why my RStudio just disappeared. Did I accidentally close that window? Here, oh, I guess I slid it sideways. Huh, that was really weird. Oh, I see, maybe because my cursor was in the wrong place. I don't know. Okay, oh, stop it. Okay. So we are going to be working through some kind of real world examples, some real data sets. And my goal is I have a few goals. One is to kind of like bring a lot of the R that we've talked about throughout the last few weeks, kind of bring it all together and sort of work through and apply it. And another is to just give some practice with real world data, because real world data is always much more complicated than sort of toy data sets that we often use for teaching R. So I'm just going to show you, I'm going to work through, well, actually, maybe I'll open. If you have not done this recently, you should probably do a Git pull. Mine's already up to date. I'm assuming that everyone here, all the names I'm seeing on Zoom look familiar. And so, oh, actually, I can't see all the names on Zoom now, because where's there. So I think everyone's been here before, and so I'm assuming that no one needs me to walk through cloning the repo or even doing a poll, but if you want me to, let me know. And so I'm going to, I'm trying to decide what I want to do first. So if you're at the main page of the repo, and you go to the data science workshop schedule, and you scroll down to today, there are actually 3 different links. So this is all the text of the document, but without any of the R chunks filled in. And then this is an R Markdown version, same as this, but with the R chunks filled in. And then here's the Markdown version of it. So I'm going to use this one as a cheat sheet, but I'm going to open this one. And so I will show you how to do that. And so what I'm planning on doing, and I think we have a good amount of time actually, I'm going to set a timer so that we'll take a break in like maybe 20 or 30 minutes, because otherwise I'll just keep on talking. Okay, so if you are in the repo itself, I'll show you what I'm going to open, and I'm going to have open in my RStudio. If in the repo, in the project, if you go to workshop 1 data science, lectures, and then I think you want, I think it's 12. No, 13, sorry. Day 13, sorry, 13 day 6 data wrangling .rmd. So that's what I'm opening here. I'm going to make that a little bigger. Oh, no, that's not right. Did I mess up? No, I forgot to leave that. Oh, no, that, yeah, sorry. Yeah, this part here is just to show the QR codes. Okay, so you can see here all the R chunks are blank, so we're going to walk through and fill them in. Let me give you a little bit of background about this material. So the data set comes from a paper that's linked, the link is here, and actually it might be a good idea to, you can either watch, I'm actually going to download to my local computer, I'm going to download the data set, because it's kind of helpful for some things to see the data is coming from Excel. It's kind of helpful to see the examples in Excel. And so if you want to also download it, I would recommend going down to line 84. Now, this is going to download it to your local computer. In a minute, we're going to actually download it onto DCC. But if you go down to line 84 and you copy this line, or you can go to even easier, possibly. Oh, wait, where did I have it? Over here? There. Here, if you go from GitLab and you click on this link here, then it will download a zip file. And then if I go, so on a Mac, oops, open in the wrong window. On a Mac, I can just double click on that and it will unzip it. On a PC, you might have to have other software installed. Like I said, you don't really need to. I'm going to open the file so you can see these are all, or a lot of these are Excel spreadsheets, and that's what we're going to be using. So, and maybe I'll try and remember which one is the first one we're going to need. We'll worry about it later. So this is data from, it's looking at how the sort of co-evolution within individuals who are infected with HIV, the co-evolution of the immune system and the viral population that's living within their bodies. And I'll give you a little bit more detail later, but that's, we don't need to worry too much about the details because really we're just kind of using this as it's a convenient data set to use, publicly available. And it is, the data ranges from a little bit messy to like kind of really messy in terms of how easy it is to analyze, like the sort of amount of pre-processing we have to do before we can analyze it. So a lot of what we're going to work on today is just like getting the data loaded into a useful format within a data frame, and then we'll make some pretty pictures based on that. So the first data set I think we're going to use is just, if I remember right, it's just tracking yeah, sorry. One other thing that I'll say is that, I guess I'm just going to move this tab here so I don't have to keep on finding. There. So we're going to, our goal is going to be to kind of like replicate some of the figures from the paper that was the basis for this data. So the first figure that we're going to try and replicate is this one, figure 1B. And we're just going to do if I remember correct, oh no, we're going to do all these, but we're going to do it a little different because I hate this figure. I'll explain why in a minute. And so I think what I'm going to do is, I'll tell you how to do a few things. And then as we go along, I'll give you, you know, maybe a minute or two to kind of think about how you want to do things yourself. And I'm going to, in case I didn't already say this, I'm working from my notes because if I was trying to do this, you know, from scratch, you know, this would easily probably take me a day to work this out from scratch. So none of us want to wait for that. So I'm using my notes just so I don't, you don't have to, and my notes are like the filled in version. And so just so you know, like if you want to like go over this later, or if you want to like go through, you know, if you mess up, whatever, the filled in version's there with the chunks filled in. Okay, so the first thing that we're going to want to do is so this is, and I'm doing things the way I would normally do it. So like I like to have at the top loading some libraries and setting up the sort of file path that we're going to use. So the first path I want to set up is for the URL that we're gonna use R to actually download the data. And so I'm going to call this LANL URL. The data is coming from the Los Alamos National Laboratories. They have a database of HIV sequences and some related information. So the URL that we're using is actually, I put it up here just so no one needs to really type this out. So I'm going to do what I would recommend you doing, which is just copy that and then paste it here. And then we're going to set up a few other things, a few directories and paths. Directories. And So the first thing we want to do is set up a Scratch directory. Oops, I can't type. And that's going to be /work, which is a shared space on the cluster. And then everyone's going to have their own subdirectory within there. And we're going to use a little bit of magic to do that. So user, if you type username equals, and here I'll explain what this is after I type it. You want to do capital S sys.info. And this is doing that for me. So it's going to magically, and then if you put double square brackets and then user, it's going to pull from the, R is going to actually like figure out what your username is and plug that in there. So if we do that, and actually we can type username just so we can see it. Yours, so mine says Josh, yours should say what your username is. And delete that part. And then we're going to define an output directory that's going to be based on that. So file.path is going to stick together a bunch of directories. The first thing is going to be this, the Scratch, dir, and then username. So this is going to make a subdirectory that's /work and then your username. And then after that, we'll just to make things a little bit more organized, we'll make a subdirectory called HIV 2024, and then subdirectory of that we'll call LANL analysis. And then we're going to make another subdirectory that's the subdirectory of that. We'll call it data dir, and that's going to be file.path. It's going to be out dir because we just defined that, and we'll call the subdirectory raw data. And then the next step is we're going to use an R function to actually make the directory, that data directory, and it's going to data dir. And if we say recursive equals true, it is going to make all the, actually, you know what? I want to do something really quick. I just want to be sure that I cleaned up after the last time when I was testing code. Okay, sorry, I didn't. Okay. So all of that is just going to make a new, it's going to assign directory path to these variables, and then this is going to make that subdirectory. Does that make sense? Questions about that? Okay. And then the next thing we're going to want to do is we're going to set up another path. I'd like to kind of make all this reproducible. So we're going to take this URL and we're going to pull off this bit here from the URL. Well, I'll just show you. So we'll say, if we just say this and run it, then that's the URL, it's just printing the URL. If we pipe that to a function called base name, what base name does is it takes a directory path, or in this case, a URL, and it takes off everything. It basically pulls out this, just the file name. So when I run that now, I couldn't find the function pipe. That's because we have not loaded any libraries. So we need to load our first library, which is dplyr. There we go. Okay. It's just telling us, since we've run this chunk a few times already, it's already created the directory, so it's giving us a little warning message that when we try and create it again, it already exists. That's okay. We can actually tell it to not warn, I think. Show warnings, false. Okay, so like I said, this base name is now just extracting this bit of the URL, and we're going to turn that into the path that it's going to, where that file is going to be saved. We haven't gotten to the part where we're downloading, but we're kind of doing some prep work. So file.path data dir, because we're gonna put it in that data directory. We need to put the dot there for the dplyr pipe, so that the value that's output by base name gets stuck here, because by default the pipe wants to put it as the first argument. So now if we run that chunk, now we have a nice path where we're going to save this as we download it. And so then I'm just gonna right assign that to lanl zip path. And I think that's all we want to do here for a moment. We're going to add something in a little bit, but let's work on getting that downloaded. Okay. Everyone okay so far? I'm hope that by me typing, it slows me down, and then hopefully I'm followable. Okay, so I'm going to scroll down here to what is now line 86 on mine, and we're going to put in a chunk of code to download that zip file that has the data into DCC, and then we're going to unzip it so that it's unpackaged. And so this is actually pretty easy to do in R. We're going to use the function download file. And because we already set up the URL and the path before, we can just plug in that lanl underscore URL. That's the URL that's going to get downloaded. And then for the dest file argument, that's what the file name that's going to be saved to when it's downloaded. So we're going to do the lanl zip path as the destination. And then we're going to add one more line, which is we're going to use the unzip function. And the unzip function is going to unzip that zip file. And we're going to put lanl zip path there. And we can tell it what directory we want it to be extracted to with exdir. That's short for extract directory. So it's just going to unzip it into that directory, and we're going to say data dir for that. And then, so now we can run that chunk, and I don't think it's going to tell us that much. I think it might, yeah, I'll just tell it was downloaded, and unzip isn't going to tell us anything. So, but what we can do in this next chunk is say list.files data dir. And now this is all the files that are in that zip archive that have now been extracted into the data dir, the data directory. Everyone okay with that? Questions? You want me to? Did that not work for anyone? Anyone need me to go over it again? Okay. I can keep going. Okay, so let's how should we do this? Okay, actually let's set up let's scroll back up here, because I want to set up a path to the first file that we're going to use. And I got to remember what I want to call it. Okay. So we're going to call it clinical data path equals file.path, and it's going to be in the data dir. And then the file name itself, I put it up here at the very top so that we wouldn't have to be typing it out. So it's on line 39, this 1362 clinicaldata.xls. I'm just going to copy that and scroll back down here. And that needs to be in quotes or double quotes. And so now I'm going to rerun that chunk so that now clinical data path is defined. And now we're going to go down. Actually, let's open. I'm just going to open that in Excel just so we can look at it really quick, because that can be helpful. That's really weird. That was not what I wanted. Somehow I clicked on one of the FASTA files, but it did open on my other screen. Okay, so this is what the file looks like. It's pretty simple. I think I already, maybe I didn't already explain. So this is one subject, one participant in the study. I actually can't remember if there's more than one participant or not in the study, but this is some sort of basic clinical data. It's recording the CD4 and CD8 counts at different times over like a 4-year period from the same individual, and then also the viral load in that individual. And so the units of the cell counts are cells per microliter, and then the units of the viral load are copies of viral RNA per mil of blood. And so this is a pretty simple table just to kind of like get us started. And so loading it hopefully shouldn't be too hard. The one trick that I don't think you've learned yet is how do we actually load an Excel spreadsheet into R? And the answer is that we can use a package called readxl, which we didn't load yet, but that's the next thing that we're going to load. Library. So I'm scrolling back up to the top where I'm loading the libraries. So line 47, and I'm going to say library readxl, and it's X, the letters X and L. I'm going to run that chunk, and then scroll back down here to line 115. And so we're going to do clinical data path. I'm going to pipe that to read underscore Excel EXCEL. And then if I run that chunk, you can see it's getting read into a data frame. So that's pretty nice. That's pretty straightforward. There are a couple of I don't know, maybe there aren't problems. Why am I? Well, maybe it's a good idea anyway. Okay, so this is like, you know, we have this as a data frame right now, and it's pretty good. But I will say that having the column names like this is going to be a little bit of a hassle. Oh, I know what it is. There. So having the column names like this is going to be a little bit of a hassle in terms of referring to the column names. So we might want to tweak that a little bit. And the biggest problem is this. If you look at the columns, so this is the day that the sample was collected, and it's listed as days post first onset of acute symptoms. and we're gonna abbreviate it as DPS as they do in the paper later on. So these 3 columns are being loaded as doubles, which is a numeric type in R. But this last column, the viral load, is being loaded as a character. And so that's sort of weird and not what we want. These are numeric values. So we want that loaded as numeric value. So one thing that we can do is we can explicitly tell read Excel that the column types are all numeric. And so now if we run this chunk again, if we look at now the viral load, copies per mil is a double, which is a numeric type. The other thing that I want to do is I want to rename these columns just so they're going to be easier to refer to as we use those chunks, use those variables. So we'll use the dplyr rename function. And so this first column, I'm gonna call that, just abbreviate it as DPS. And I'm gonna be really lazy. I'm just gonna copy this here. So DPS equals, and you need to use a backtick because there are spaces. And the backtick on my keyboard, the backtick is upper left corner. It's the same key as the tilde. And I'm looking at a Windows keyboard that's next to me for the room computer, and it's also on that same key. Okay, and so I'm going to just run that chunk and see if it worked, and then we'll keep going. So yeah, so that's working fine. So the first column is now called DPS. So I'm psyched about that, and we're going to just keep on doing that for the rest of the columns. So the next column, I'm going to call it CD4. And again, we need to do a backtick. And I'm going to copy this. I'm trying to copy it without copying anything else. And I'm just going to do the rest of them right now before running it, because hopefully it'll work. Backtick, and I'm going to copy this. And that worked pretty well. If you triple click here, that seems to work well. To highlight it. That's it. Yeah, highlight it. And then the last thing, I'm going to call it virus equals, and then backtick, and then triple click there, copy, paste. And now I'm going to run this and see. So yeah, so now I've got my columns DPS, CD4, CD8, and virus. They're all doubles, and it looks like a nice, all looks good. I guess if we wanted to, we could just double check all the rows, and they all look normal. So I'm happy about that. Okay, and then the last thing I'm going to do is I'm going to do a right assign to a variable. So I'm going to call that clinical data underscore DF. And then just so that we can actually see the data frame again, I'll run that. And we can see the data frame. There's some message here. Coercing text to numeric in D17. All right, so that is possibly why it was loading it as a character vector. D17, all right, row 17, C4. Row 17, C4. Now, there's probably a space there. Oh, I don't know. I don't know why it decided that that's it's something funny about this is, yeah, in the Excel spreadsheet, this is stored as text. Yep. All sorts of weird stuff happens in Excel. Okay. So does everyone have that data frame loaded? Anyone need me to go over that again, or haven't getting an error message or anything? Okay, and now remember, our goal is to take that and make this figure. Okay, so not going to be too hard. And get rid of that. So, so not too hard, but we need to do a little bit of work because we're going to use ggplot, and ggplot isn't going to like the data in this format. It's going to want, ggplot usually likes data in long format. So we're going to use tidyr, which I think you've covered, and we're going to make it longer. So we're going to do clinical data df, and we're going to pipe that to pivot longer. Actually, you know what? I'm going to, well, no, let's do it this way. How about we take a, let's take a 5-minute break. Let's take like a 5-minute break. Spend the 5 minutes like taking a break, but then also thinking about how to, well, you can aim, I'm not expecting necessarily anyone will get this, but think about how you can make this longer. And I'm not going to tell you anything about how I would do it, but I'll do that when we get back. But think about how you make it longer, and then if you're really ambitious, you can try and make this plot. I'll actually give you a hint. I'm not going to make. Well, we'll start off making this plot. Actually, we'll start off just making a plot of the points without the lines connecting them, and then we'll and actually just one axis. This has 2 axes, which I don't like. But we'll just have one axis for starters, and then we'll make a nicer version. So yeah, so we'll take a 5-minute break. I have 2:07 now, so let's aim for I don't know, let's take an 8-minute break. We'll aim for getting back at 2:15. So the answer is kind of complicated because everything is, for people on Zoom, the question was, do I find it easier to do on a Mac than on Windows? So everything's being run on GCC. And when I do data analysis, or like anything computational, I'm always running it on GCC. And so in that case, it's doesn't matter too much. I mean, I feel like some of the web browsers are kind of funny on Windows for like copying and pasting. But other than that, it's pretty similar. I think for a lot of other stuff I do, I like a Mac better. There was a point in time when I did a fair bit of computation on my computer, in which case it was easier to do stuff on a Mac, but like I said, I almost always do stuff on the cluster. It's pretty rare that I do stuff actually locally. Okay, so it is 2:16. So does anyone want to volunteer what they did? And if you didn't get anywhere, that's okay too. I think it's useful to like, even if you can't figure out the answer, it's useful to kind of ponder. No volunteers? Okay, well, like I said, like a lot of this stuff, I couldn't do it off the top of my head necessarily anywhere nearly as quickly as I'm typing it here. That's why I have notes. Okay, so what I want to do is have, so I want to have, what I'm aiming for, I think, if I remember correctly, is to have the dependent variable be this DPS, and then all the rows will be, I'll have a indicator column that tells me which type of data it is, and then another column that tells me the value. And so for pivot longer, I'm going to say calls equal minus DPS. So that's going to get me everything except for the DPS column. It's going to get like made longer. And then we'll say names to equals assay type. So that's what the new column is going to be that says either CD4, CD8, or virus. And then values to equals blood count. And that's going to be the actual numerical value. So we can just run that chunk. Oops, didn't like that. Could not find function pivot longer. Yes, because I forgot to load tidyr, library tidyr. I'm gonna rerun that chunk. And actually a few things I didn't mention before. So one is I like having these values, the library and the paths up here because it makes it easy to find. I do that pretty consistently, and so I know where to go to look for those things. The other thing I want to mention is that, downloading this zip file and unzipping it with code is maybe like a little bit more of a hassle, but what it does, and actually some other things like defining the paths here, what they do is make the code pretty reproducible and also pretty portable. So like if I wanted to run this, like on my laptop, for example, I could just change like this scratch dir. I'm not sure if the sysinfo, how well that would work on my laptop, but I can just maybe like delete these two things and put in something else here, the directory here, and then everything else should actually run pretty much on any other computer that has R installed, or R in RStudio, and it's got to have the libraries installed. Although also you could run it in I think I mentioned before, everything we're doing is actually running in a Singularity container, so you could actually just move that container onto another computer. Anyway, that was just a little bit of an aside, but there are some things that I'm doing I want to point out that are for the sake of reproducibility. Okay, now I'm going to try running that again. Good. So this is what I was looking for, right? So the first column is the DPS, the days post onset of symptoms, and then I have this column that tells me which type of data it is, and then this is the value of that. Okay? Questions about that, or should we take a first pass at looking at the data? Okay, so now I'm going to pipe that directly to ggplot, and so aesthetic, the X value is going to be DPS, the Y value is going to be blood count, and then we'll color points by assay type. And then we're gonna do a scatter plot. So we'll do a geom point. Couldn't find function ggplot because we need to load it. Okay. Library, gg, plot. Run that chunk again, scroll back down here. Okay, so this is like kind of a big mess. Actually, well, let's make it maybe a little bit better. We can also add a geom line on top of that. Let's see if that makes it better or not. Yeah, so that's well, it does solve, like, I don't know. I feel like it does make it a little bit better, right? So we're actually like part way there. The virus actually looks pretty, I pushed the wrong button there. The virus actually looks like not too bad. That's the viral, no, it looks, oh no, yeah, it looks about right. This looks like the viral load figure here. This figure actually doesn't plot the CD8. Sorry, the CD4. It just plots the CD4, not the CD8. Here we're getting the CD8, but we're not getting the CD4. Any idea why? And also it's a flat line. That's kind of a hint. Yeah, it's too. Yeah, so the values are, so the key difference between this and this is that this has two different y-axes. So the viral load, the order of magnitude is, in the order of like 10 to the fifth, whereas the CD4 counts at least are on the order of, 10 to the third. So when we're plotting it here, the range of values for virus are, around 10 to the fifth. And these values are all kind of stuck at the bottom, right? So we need to fix that. I don't want to fix it this way because I'm not really a big fan of like having two axes on a plot. I think it makes it a lot harder to interpret. I mean, when I like first looked at this plot, I was like, what's going on here? I'm confused. So I want to do things a little differently. And the reason why we don't see any CD4 is because the CD8 and CD4 are like basically near zero here. And yeah, so CD8 is on top of the CD4 values. If you look really closely, you can maybe see the hint of a little red at the bottom of that CD8, the green. Okay, so let's make this a little bit better. And I'll just do it in that chunk. So for starters, let's do, let's see, what do we want to do? Okay, so for starters, let's just make this a facet plot so that we're going to separate those. So there is a way in R to have two axes. I don't remember how to do it because I don't like it. So we're gonna start things off and we're gonna do a facet plot, which is gonna divide this into three plots. I think it's gonna look nicer and it's gonna be simpler. So we're gonna do facet wrap and do it by, so we're gonna facet it by assay type. And actually, let's just run that chunk and see how it looks. Okay, so I think that that's like actually a little bit of an improvement. Not much, because we divided things up. We're still stuck at the bottom here. But we divided things up, so I'm feeling better about that. So one thing I want to change is that I'd actually like to kind of stack it so it's a little bit more similar to this, because really we want to, I want to be able to compare like at the same time point. So we can, one way to do that that's pretty easy is to just specify the number of columns. So we're going to force it to have one column, which will then split it up into rows. So there, okay, now we can actually at least compare, the same time points. It's not helping us. We haven't solved the problem yet that these all look like zeros, but that's actually pretty easy to solve too. We can say scales equals free Y, and that just allows each of the facets to have their own separate y-axis, because it's free y, so it like disconnects the y-axes of the different plots. And so now, if you compare that to this, and remember, we're just looking at the CD4 and the virus because the original plot doesn't have CD8. So that's pretty good. I mean, we've kind of, you know, we can flip back and forth, but I think we're doing a pretty good job of replicating it. I mean, the limits on the y-axes are a little different, right? This one's CD4, that's starting at like 800, and here it starts at like, say, 0. If we wanted to change that, we could, but I don't really care that much. I think there are a few other things I'd like to fix about this, but like, I'm actually pretty happy with it already. One thing that I'd like to fix is that the axis label here isn't very informative, because these are, I mean, it's blood counts, sure, but I'd like to actually know the units. And so I'm going to, we'll be a little bit lazy about this. So this is getting a little bit fancy. I had to look this up, by the way. So if we say labeler equals as labeler C CD4 equals, I'm just going to do one at a time. So CD4 positive, CD4 positive cells per microliter. So this is basically, it's just going to add labels to the y-axes. And it's saying, okay, for the CD4 plot, the y-axis should be CD4 positive cells per microliter, or UL. You get the idea. Oh, not working. Why is it not working? Oh, maybe because I need to do this plus Y lab. Oh, possible I messed something up. Acid wrap free labeler as labeler CC4 equals. Okay, let me see if, that's why. No, maybe it's not why. Sets. Here, let's try that again. Nope. Do I need to have all of them in there? Let's see. CD8 equals stuff. Oh, yeah, sorry. Now I know why. It's actually labeling it here. Oh no, that's what I wanted. Is that what I wanted? Yeah, no, I think that is what I decided to do. Okay, sorry, it's putting the label here. So it's not labeling the y-axis. I forgot. Okay, so we'll do the same thing for CD8. I'm just going to copy and paste and be sure I change it to CD8. CD8 positive T cells, and then virus equals viral load copies per mil. Okay, so now we have this nice, nice labels. We can, if we want to make it a little bit more like this figure, we can change the x-axis to, you know, be prettier. So we can say plus labs, because right now the the x-axis, right now the x-axis just is DPS, which isn't super informative. You say x equals days post onset of acute symptoms. And then so that's nicer. And then just to make it a little bit nicer, I'm going to do two things. Well, I'm going to do three things. First of all, I don't really like this theme. I don't like the gray background. So we're going to do theme, the black and white theme, which I think is a little bit nicer. I'm not super fan of these titles, how they are, but I'm going to leave them. We don't really need this, the legend, because it's pretty clear, you know, it's only one value per plot. So I'm going to get rid of that. Theme, legend, dot positions, dot position equals none. So that'll get rid of the legend. And then the one other thing that we could do that Edward Tufte would say we should do is we don't really need the color here because each of these plots is a separate thing. And so if we want to Tufteize this, we would get rid of the color. So that's just deleting in the aesthetic here. And then it'll just be black. I'm happy with that. Questions, comments, anyone not like it? Anyone see something else that they think we should change? And if we wanted to, we could get rid of the CD8 values because those aren't the original. But so I think this is actually a way better version than this, in my opinion. But you know, again, that's my opinion. Anyone not ready to keep going?
Hey, Josh.
Yep.
So how would you make it say start at 0 across all of them if you wanted to do that?
Like you mean have it be like?
We'll have the Y value start at 0 since it looks like in the figure they have the Y start at 0.
Yeah, it's a good question. I'm not entirely sure off the top of my head how to do that. Like I know how to do it for, like I think we could say if we wanted to do it for, we can try. I think it's Y lim 0. Again, this is something that I would need to look up. I don't think this is going to work, but I'll try. I think it's going to give me an error because I think I need to give it like a pair of values. Yeah.
Okay. I was just curious.
I'm sure there's a way to do it, but I don't know. I don't know how to do it now that we've fasted it. Yeah. See, it's like a nightmare. Yeah. Sorry. I didn't worry about that. I figured it's better to actually like have it. I don't, you know, who knows why they choose those ranges. I'm sure we could figure it out if we really care. Other questions? Okay, so the next task is figure 3, which is, let's look at that. Get rid of this one. So, and we're not going to do the whole thing. We're just going to do the CTL, the cytotoxic lymphocyte response, which is in red. And we're going to do, this is actually like 2 sets of, like they divide the data into kind of 2 sets. And so the first set I think is A through H. And we're just going to do those because it's otherwise we have to like load another spreadsheet and stuff like that. And I'm not even going to touch the sequence frequency part. We're going to have enough to deal with just getting this because as you're about to see, the data is really ugly. So the data for this is, let's see. Okay, so strongly selected epitopes. So I'm going to open that. strongly there, this one. And of course it opens in the wrong, on the wrong screen. Okay, so here's the data, and I'm just gonna, so it's kind of weird because, and it's gonna get worse. If we have time, we're gonna get to a third spreadsheet that's even worse. So there are a couple of issues here. And I'm not even gonna point all of them out to you. But so one of the weird things is that there's two headers for each column, right? And these are actually like, this is kind of like the subtitle for it. And there are a couple of ways of dealing with this. And we'll see what to do. What we're gonna aim for is actually to kind of merge those, because in the original figure, it actually does have both of those in there. So we're going to try and pull both of those out of the spreadsheet. But it's going to require a little bit of magic. So let's start off. Actually, the first thing that I want to do is I want to go back to the top, and I want to define that path, the path for that. We're going to call that strong selected path. Oops. File.path. And do just what we did before, data dir, and then I'm going to go up here where I have my notes, and that is strongly selected epitopes XLSX. And the name of the file comes from the fact that these are like viral epitopes, like specific parts of protein, which based on like some analysis that they did in the paper, there's like strong selective pressure. The immune system is putting strong selective pressure on those epitopes, and so the viruses are evolving away from those epitopes. Okay, so I define that up here in my path section. I'm going to run that chunk again. And then we'll scroll back down here to, actually, I need to do that and use this. So if you click on the little thingy down here, you can navigate to different headers. So I'm going to navigate down to figure 3. Okay. And where are my notes? Okay. So let's just do like a simple first pass at this and just load it in Excel. Or sorry, use read Excel to load the that data and see what happens. It's not going to be, we're not going to be super happy with it, but it's a good starting point. So I'm just going to pipe that to read Excel. Okay. So here's what we get for starters. The header is DPS, and then we see like the header for this is magnitude of CTL responses, SFC per 10 to the 6 ppmcs. And then here we get this weird stuff with that .3, .4, .5, .6. And then, so here are numbers and here's some other stuff. So, and anyone have any idea why, what's going on there? Switch back here. So what's happening is that, well, there are two things happening. One is that there's this first row here. It's actually a merged row. It's a bunch of cells that are merged. I don't know if everyone's ever seen that before in Excel. You can like take multiple cells and merge them into one. So it kind of like centers it. So read Excel, just like read CVS, it assumes that the first row in the file is the header. And so it's treating that as the header. But this is really like actually the kind of, I mean, this is telling you what the values are. Like if we look here at figure 3, that's really essentially the y-axis, or at least the y-axis for the red value. So that's not really what we want. And the other thing, if you notice, it's got DPS, there. So these are merged cells too, that's got DPS, that's the days post onset of acute symptoms that we saw before, right? So this is days. And then these are measures of like basically how strongly the cytotoxic T cells are responding to those different epitopes in an assay where they're using these short peptide sequences to like test those T cells. So this isn't what we want. And the other thing I was these like .3.4 or .3.4 is basically read Excel is saying, okay, well, there's nothing, we don't have any header in this column, so I'm just gonna call it basically column 3 column 4. That's not what we want, right? We want this stuff as the column headers. Okay, so that I don't think I'm going to ask you to try and figure out how to do that because this is getting a little bit like funny here. I think I'll just show you. So we can just do it here. The first thing that we want to do is we want to skip the first row. That row that has the magnitude of CTL responses, because we don't care about that. We'll come up with that y-axis label later when we're actually making the figure. So we can say skip equals 1, and that's just going to skip the first row. Okay, so this is a little bit better because now we've gained something, we've lost something. What we've gained is now we're getting this, this column, this row as our headers. But then the second header row is showing up as a value. So that's what we gained. So we're getting closer, but this isn't what we want either. And the thing that we lost is now this column is no longer labeled DPS because that was in the first row. So we're gonna have to fix that. The way that I decided to fix this is to actually kind of deal with making a new header first, and then we'll kind of deal with the rest of the data later. And so what we can do is we can extract the first 2 rows and then kind of like munge those together. And then we can load the rest of the data and just supply read Excel with this sort of pre-made header. So for starters, we can just extract the first 2 rows. So let's do that. So we can say, okay, we only want the first 2 rows. So that's n max is 2 is saying we're gonna skip the first row. We're gonna then get the next 2 rows, right? So skip 1 and then just load in the next 2 rows. So that's, oh no, it's loading values. Oh well, we'll worry about that later. Okay, so that's kind of partially getting us there, but really we don't really care about this first column for now. And actually, well, we don't want this row anyway, but we don't care about this first column right now. We just want to deal with the names of the different epitopes. So we're going to do things even like slightly differently. We can tell it to load a specific range of cells. And so to do that, we do cell call B through I. So this is that, if we go back here, this is column B. And so this is going to load just these columns, and we're going to ignore this first column here because we're going to, like I said, we would just want to grab this bit. So that is going to get us, well, it kind of helps. It's, for some reason, read Excel, now that we're saying, giving it a range, it's ignoring this n max equals 2. So it's just loading columns I through H, but it's not, it's giving us like the full data set. So we got to do something about that. So we may as well just get rid of this n max equals 2. That didn't really help us in the end. And then the way we can just get the first 2 columns is we can use the base R function head and say head 2 is just going to get us the first 2 rows of that data frame. Okay, so now we've got, no, it's not even doing the skipping. Why isn't it doing skipping? Oh, well, we'll deal with that later. Okay, so now we've got these, the sort of two rows that have the epitope information in it. That makes sense? Questions about that? Okay, I'm going to keep going. Okay, so now the way that I think is an easy way to do this, because like I said, we want to kind of like stick these, we want to stick this row, this value with this value. And like data frames, dplyr, like anything in R, like it doesn't really like kind of want to, you can kind of work column by column, but it's harder to work row by row. And so one easy way to solve this is we can transpose the data with the T function. And so we're just going to flip this. So now we have these values as, you know, adjacent columns, which R is going to be happy to deal with. Okay. And then now, so transposed always gives you a matrix. So we have that data frame. Now we transposed it into a matrix, and now we want to get it back as a data frame, or really what we're going to do is make it a tibble, but you know, kind of same, the tidyverse version of a data frame. So now we have this tibble with the, you know, the transposed version of the header, and we can use a tidyr function called unite, which will basically allows us to stick 2 columns together. We have to tell it what we want our new column to be called, and I'm going to call it combined calls. Very creative. When we turned into a tibble, it labeled these 2 columns as V1 and V2. So we're going to say, you know, no need to like rename those, because we're just going to like stick them back together. And then our separator, this is basically what's going to be between those 2 values. So just to make clear what this is, I'm going to use a, I don't know what I want to do for starters. We'll put a $sign in there for starters, just so you can see what's going on, and then we'll fix it in a second. So now we have, see, we have this new column where the 2, what were 2 columns are now pasted together with a $sign in between them. Got it? In a second, I'm going to leave that there for now. In a second, we're going to change what the separator is, but let's finish up and then we'll do that. Okay, so now what we want is we want this as a vector, because we're going to feed it into read Excel to be our new header. So I'm going to use the pull function from dplyr that just, it takes a column out of a data frame. Here we only have 1 column anyway, but it's just nice because it pulls a column out of data frame and returns it as a vector. So we'll do, so we're going to do the combined, if I can spell right, combined calls. Okay, so now we have this Now we have it as a vector, and I'm going to right assign that to epitope header, and then we can just print it because it's nice to print it things out. Okay, so that's pretty good. I'm pretty happy about that. The one thing that I was gonna, so now we have this as a header, or as a vector, we can feed it into read Excel. The one thing I'm gonna change is I'm gonna make that separator this, which is a new line. So in, where's the figure? There. In this figure, it shows like the first part, the like epitope, the peptide sequence of the epitope on one line, and I think this is like telling you the position in the genome of it. It's got this other stuff that tells you like what the gene is, and I don't know what all the notation is. I guess this is the position in that epitope that, sorry, like this is the TAT gene, and I think 30 through 37 is actually the position in the TAT gene of, sorry, in the TAT protein of these amino acids. If that doesn't make any sense to you, that's fine. We're not really like, we're not getting into the details of epitopes today. We're just like trying to recreate the figure. Okay, so now I'll just rerun it. You can't really hear it's just showing up as \n, but when it actually gets printed in the figure, it's going to put this part on a separate line, which is exactly what we want to be able to replicate this. It also will make it, otherwise it's going to be like really long, and trust me, we'll be happy about it later. Okay. Questions about that before we keep going? So that was like the hard part, I will say. The rest is actually not so hard. Well, at least loading in the data. So I have some extra stuff here. Yeah, so let's do here. Okay, so we're gonna reload the data. Strong selected path. We're gonna run read Excel. So here we're gonna skip the first 3 rows because the first 3 rows are all this header stuff, and we've already kind of separately dealt with the header stuff except for the DPS part here. We just want to load in this stuff. We're going to skip the first 3 rows. Skip equals 3. Let's see what that looks like, right? Okay, so that's pretty good, except now it's actually getting some of the data, but that's okay. We're going to give it a, we're going to tell it what the header should be. Call names. So we want the first column to be DPS, right? And then the rest of it's going to come from this, what we just made, the epitope header. Epitope header. And now we have this nice kind of normal looking data frame. So that's pretty cool. We do have actually, if you look really carefully, we do have a few problems. So one problem is, at least here, remember how we had one of the columns that loaded as a character vector or as a character type, right? So here that's happening again. So there's an easy solution for that. Before I tell you, well, does anyone know that the solution? We already did it before. And the other question is, why is this getting loaded as a character type? Everything else is a double, which is what we want. Okay, I'll give you a hint. If you look at the original spreadsheet, and another hint, if we keep looking down the columns, Yeah, it's got at the very bottom here, it says DPS is days post onset of acute symptoms. And so that's not like, this is again, like one of the things about Excel that's a problem is that, you know, people feel tempted to put that sort of thing in there. But then when you try and load the data, Read Excel is saying, well, okay, like 1501, I can make that a number. DPS, date, colon, days post onset of acute symptoms, I can't make that a number. So, so we have two rows in here that are being loaded that are kind of garbage. There are different ways we could deal with that. The way that I want to deal with it is to force this column to be a numerical value. Any thoughts on how we do that?
We did the column types.
Yeah, so we can do column types and just say numeric. I believe, if I remember correctly, you can like have different types for different columns, but so you can give this a vector, but if you just give it a single value, then it'll make all the columns numeric, which is what we want and saves us some work. So now this is a double, which is what we want. And if we go to, if we go down to the bottom, now that what had the text before is now being loaded as an NA. So we need to deal with that, but we don't necessarily need to deal with it. Well, okay, we can deal with it now. It's probably a good idea to deal with it now. Okay, so we're just going to filter out rows where there's an NA in the DTS column. So filter not, that's the exclamation point means not is NA CPS. So basically any row, it's going to filter includes things for which this is true. I think there's a way to make it the inverse, but whatever. So now if we run this again and we look at the bottom, it just doesn't, it just dropped those rows. Okay, that's what we want. We can assign that to strongly selected data frame, and I'm just gonna put that again at the bottom so we can print it. Okay, so we got our data loaded. Now we're gonna make a figure. It's 3. How about let's do this again? How about we'll do the same thing. Aim to make a figure. So the strongly selected, if I remember correctly, let me see if I have it in my notes. I think that, yeah, so we just want to do, the data that we loaded is just E through H. And remember, we just loaded the CTL data, so that's the red line. So let's take a 10-minute break. Maybe we'll make a 5-minute break because I need to leave time at the end of the survey. So let's take a 5-minute break. We'll aim to be back about 3:05. See if you can make this figure from what we did already. I'm not expecting anyone to get it done, but you know, see what you can do. Anyone want to volunteer what they came up with?
Similar to what we did the first time. So it's just like crazy graph.
Okay, you wanna walk me through it?
Sure. What I did is we
Actually, can you push the button so that?
So what I did was we did the strongly selected DF with the thing, and then the pivot longer columns equals the DPS.
equals DPS like that.
The minus D.
Oh yeah, minus DPS. Yep.
And then names underscore 2 equals in parentheses epitope.
So underscore 2 equals
Or sorry, not parentheses.
quotes.
Yeah.
Epitope. Epitope.
And then comma values underscore 2 equals in parentheses CTL. Yeah, all caps CTL.
Okay, I'm just going to run that for starters. Okay, that's looks good, except they're a bunch of NAs, but I think that that's how the data is. So
And then next line was ggplot AES. And then another like parenthesis X equals DPS, Y equals CTL, and then comma color equals epitope.
yeah, plus, yep. Point. Okay. Oh yeah, you do actually. You're right. I can run that. Okay, cool. Something. Do you have more? Or is that as far as you got?
And then, I mean, you can go further to break it up into the brackets or the like boxes, I guess. You could also add the lines if you really wanted to.
I would love to add the lines.
Oh, so then you have.
Well, you can do the keep going what you have, and then we can.
Oh. Well, the lines would be the geom underscore line
Okay.
brackets.
Yep. Okay, looks good. Yeah, well, I only gave you 5 minutes. So that's, okay, so that's great. Did anyone else have anything else? I mean, this is like, 99% of the way there. It's just kind of cleaning up from here. Okay, so again, this probably took me a good half hour to an hour to do this. But yeah, no. Okay, fine. It maybe like took me like a little bit less because I'd already done the first example. But okay, so the next thing I'm gonna do is doing a facet wrap. And we'll do that by epitope. Let's do it by epitope for starters, then we'll make it a little bit fancier. Ooh, it didn't. Oh, because I made it. Yeah, that is right. Okay, so that's pretty good, right? Oh, and actually here, I'll just show you, this is, remember, like, that's what, we have this on 2 lines because of the, because we put the separator up here as a, where is it? The separator is N. If we like instead put the separator as like, say, a comma. Now let's make it a semicolon. I'll kind of rerun that chunk, see there's a semicolon there. And then here it's going to have the semicolon there. And there it's going to have these like terrible headers that you can't read. So that's why we did the new line. It actually puts it on a new line. That only took me like 20 minutes to figure out. Okay. So the facet wrap is kind of most of the way. Minor other difference is we can, again, this is getting like sort of picky, but this is 4 columns, so we can do that. You can make it 4 columns. Actually, sorry, let's do, let's get rid of the figure legend first, because that's taking up a whole lot of space. So theme, legend, position equals none. Okay, there. Feels way less crowded already. And actually, I'm gonna change the theme to black and white because I just can't stand the default theme. So we'll call theme black and white, make it a little bit simpler looking. Okay, and then we can make it 4 columns just by saying, if you remember before we said n col equals 1, but we can make n col equals 4 and force it to have 4 columns. So that's pretty good. And then the one other thing that I have is just fixing the y-axis so that it looks the same as this figure. So it's got this huge y-axis label. So we can do that. That's not a big deal, except for it's a lot of typing. Labs y equals magnitude of CTL responses SFC per 10 to the 6th PBMC. And that's it. And now we have, like, you know, it's not there. Oh, actually, there, why am I not? I know. Okay. I have 2 other things to do. One is, if we want to make this more Edward Tufty, we can get rid of the color. Because it's not really doing anything. You know, we already have it separated by box. So the color doesn't tell us anything additional. And the other thing, I'll see. Does anyone notice anything funny? About the figure? Yeah, well, you answered that question, right? Yeah, so there are some points that aren't connected, and that's because there are some NAs in the table, and so it's not going to connect the NAs. Any idea how we fix that? It's actually really easy. Surprisingly easy. I'm not saying. So we can just filter out NAs. Filter is NA CTL. I think there was probably a nicer way to do this with dplyr, but I can't remember. And there, now we don't have those. The NAs are gone, so it's connecting points. And it just had the NAs because if you look at the original, it's just that, like, for some of the time points, they don't have, like, data on all of them, right? Which, you know, like, you can imagine, like, okay, well, like this time point, they happen to, like, you know, they just assayed this one and they didn't assay the other ones. So, you know, that's okay. Okay, so that's pretty good. Like, I'm psyched about that. Any questions? We could fix the y-axis, but in the original they had it as DPS in this, like, kind of weird location. So I say we just leave it like that. Questions, comments before we move on to, like, the worst monster of the data sets? Okay, we can keep going. So the next figure is figure 7 something, 7B. So here's the figure. And so this is a kind of like a weird figure in that this is figure A is this column, figure B is this column, and figure C is this column. This is looking at like this is sort of the original epitope, and they're kind of like looking at how it evolves and how the like T cells are responding to it over time. And so we're just gonna, I just picked out one of the columns to make just because otherwise we have to like kind of combine data across spreadsheets and stuff. And I didn't think we'd have time for that. So we're just gonna remake figure B, which is this column right here. And for that, we need, it's, come on. I think it's this spreadsheet. And of course it's popping up on a different screen, right? And so we're actually not going to use all the data in this, but it's basically, we're going to use one of these. So the way that the data is, it's very confusing. So this is like the original isotope, the original epitope that was identified in the virus, and there was a T cell specific for it at some point, and then they've collected like variants of that. I guess it's variants of the viral sequences. That basically the virus has evolved so that it's you know, these different variations of this peptide that's right here, so that it's, you know, not recognized by those T cells. So this is like the whole problem in HIV of like, you know, it's continuously evolving very rapidly, right? So this original here corresponds with all these variants here, and then here's another original and one variant. Here's another original and several variants. And I can't remember which, we're just gonna use one of these sets. I think it's this one, this X through AB, but we'll worry about that a little bit. And so this data is like even uglier because now there are 3 rows of headers, right? There's what we had in the last one, these sort of like, you know, 2 lines of header here, but now we've got to deal with this original versus variant thing. And this is like we had in the first one, oh no, second one, I don't remember, where we have this merged cell. So this is merged across all of these because all of these are variants. So it's going to be like a real, it's going to be a real headache to deal with. The first thing that I want to do is go all the way back up to the top, and we're going to add that path. So this is the file name here, variant env epitope. So all of these are in the env protein or the env gene. And so I want to call this env epitopes path. And we're going to do the same thing we did before, file.path data dir. Oops. There. I'm going to paste what I just copied up above. So that now, further down, let's see. Use this. Go to figure 7b. There. Okay. So now let's just load that with read Excel and see like what kind of nightmarish scenario we have, and then we'll work from there. Read Excel. Okay. So like, not surprisingly, this is kind of looking like what we had what we had last time, where like the first row is it's getting the DPS thing here, and it's getting this huge merged magnitude of CTL responses thing here as the other header. And then now it's got the .3, .4, .5, you know, that's terrible. And then, but the problem before, when we had the merged cells, we kind of ignored them because we didn't really care about this. You know, that we can just add in later in the figure. But now we've got to deal with the, you know, we have the variant merged cells, and read Excel is just, for this variant, is just assigning it to the first cell in the first row, no, sorry, the first column in the set, right? Whereas here it's, you know, this variant applies to all of these columns here. Read Excel is just like, for the rest of the columns, you don't know that's variant. I mean, I guess you could kind of figure it out, sort of. You could fill in variant in all the columns. But I think there's a better way, and that's to, like, for the moment, give up on read Excel. Because there's another R package called OpenXLSX. It's another package for loading Excel spreadsheets into R. It's not quite as like simple. It's more powerful, but that also means that it's like harder to work with. But it is going to do a better job. It has a built-in functionality for dealing with these merged cells that's better than read Excel. So we're going to at least deal with the header using OpenXLSX. And we're going to do kind of what we did before, which is like fix the header and then go back and deal with the rest of the data. And so we're going to load this with a function that comes from OpenXLSX called read.xlsx. And it's not going to work right now because I have not loaded the OpenXLSX library. So I'm going to go to the top here. Say library open there, OpenXLSX. I'm going to run that chunk again. And then I'm going to navigate back down here to figure 7. Here, this chunk, read XLSX. And we're going to use the fill merged, I didn't spell that right, fill merged cells parameter true. So basically what that's going to do is it's going to push the, here where variant is just showing up here for read Excel, it's going to actually kind of expand it to all the columns that it's on top of. So you'll see, actually, what we can do, let's try it, like, let's actually do it first without, see what happens. I think it's going to give us a kind of nightmare. Yeah, so here, it's like variant isn't getting filled. If we do fill merge cells equals true, then now magically you see variant is getting spread to the right, to all the columns. So that's like, that helps a lot. The next thing we're gonna do is we're gonna run it with another parameter, call names equals false, because right now it's spreading this magnitude of CTL responses across all of them, and we don't really care about that. And so I think I actually creates a problem for us later. I can't remember why. But, and you see it's actually spreading the DPS down because it's filling in all the merged GPS cells. Okay, and so this gets us a lot of the way to what we need. So we're gonna assign that to a variable and epitopes raw. And now we're gonna do the same sort of magic. I'm just gonna run that chunk again. And now we're gonna do the what we did before, which make a new header, and then we'll like actually load in the rest of the data. So I'm just working a new chunk here. So we're gonna take that env epitopes raw. We're just gonna take off the, we don't want this row. We just want these 3 rows, the one that has the original or variant, and that has the epitope name, and then it's got the second part of the epitope thingy there. So we're gonna, remember before we used head, we're gonna use another function, slice, that allows us to do like, not the beginning 2 rows, but like the 2nd through 4. And so that's exactly what we want. We want those rows. And then we're going to do the transpose again, just like we did before. So now we've got a matrix and got transposed. And by the way, I don't know if you noticed this before, I'm just being reminded that this like kind of more detail here is not included in the subsequent ones. I'm not sure, I'm actually not entirely clear. I think that's just the way they did it, but if we look in the figure, they also aren't showing that, right? So that's okay. And then the other, actually, we'll get back to that. Okay, so we're going to do what we did before. We're going to make it into a tibble. And then we are going to do exactly what we did before, which is do unite, combined calls V1 through V3. So it's the same as before, but now there are three columns because we transposed them. And here we'll make I think we want to make the separator new line again. That's not what I have in my notes, but I think that's what we want to do. Okay, and so there, now we got this. So that's getting us partway there. And we're going to do then pull that like we did before. Combine calls. And we'll right assign that to env epitope header. Oh, didn't like that. Because I misspelled combined. There we go. Okay, so now we're kind of like, we're pretty good. Do we want to deal with this now? No, well, I don't know. Should we make it cleaner first, or now? Let's make a figure first, then we'll clean things up. Well, I don't know. Yeah, I'll just clean it up. Okay, so there's some weird things going on in here. Anyone notice weird things going on? No one? Nothing? Okay, fine. Let's skip it for now. We'll come back to it. Let's load in the data. Okay, so now we're going to do what we did before. We're going to use read Excel, and we're going to assign it the header. So epitopes path. I mean, we're going to like, give it our custom made header. So we're going to say read Excel. We're going to skip the first 4 lines this time, right? Because we have that first row that's just like really the y-axis label. And we're going to say call names equals and epitope header and call types equals numeric. And there's a little bit more cleaning up we could do, but I think I'm going to skip it for now. And then we'll do env epitopes data frame. Okay. So how about this? Anyone see anything weird about this?
It still has the NAs, like in the names.
Yeah, it's got the NAs. Should we get rid of the NAs? Yeah, so the NAs are from these things got loaded where, oh no, not that. Oh, I'm looking at the wrong spreadsheet, that's why. Yeah, here. These things got loaded as NAs. And you can see that here, yeah, here. So that, this 4th row here, for the original, it's got something, but when you get to the variant, it's got an NA. So we can get rid of the NA. That is, when we do the unite, we can say na.rm equals true, and it will get rid of NAs for us. So now we've got rid of some NAs. Anything else you notice funny while we're looking at this? Not necessarily obvious. Not super important, I'll be honest with you.
I'll throw it out there.
Yeah, throw.
You're gonna want to maybe squish those strings a little bit. Also, this is a minor thing.
What do I want to do?
Squish the strings. There's some trailing white space.
Yeah, trailing white space. Yeah, exactly. See here, there's like a space there before the double quote there. There's also a few other places like, I mean, here it kind of makes sense, but here there's a space before the new line because the new line got stuck in there. So we can get rid of that with, and to be honest with you, I feel like it ends up being noticeable in the plot, but I don't remember. I think it messes with the, actually maybe let's leave it for now and we'll come back to it because I remember it shows up somewhere, but I don't remember exactly where. So yeah, so maybe I'll just keep chugging through. We'll try to make the plot, see if we have time. This is going to be pretty similar to what we did before. I'm going to pivot the data. If you want to figure it out for yourself, you're welcome to like cover your ears and just ignore me for a minute, or you can just come back like tomorrow and do it. So we're going to drop we're going to like, make all the columns longer except for the DPS column, just like you did before. Names to get, names to is epitopes. Values to is CTL. Actually, let's look at that. So I'm getting a problem. Column DPS doesn't exist. Why is it saying column DPS doesn't exist? Any thoughts? Yeah, we got 3 DPS because when we did the like merge, when we did the fill merge cells, it spread the DPS down, and then we like merged up columns, and so it just gave us a repeated DPS. So that's one of the things that we didn't fix before. So let's fix that. And the easiest way, I mean, the way that I decided to fix it, there are probably other ways to do it, is just to do a string replace. This is a function from string R. So it's DPS, DPS, DPS. And we're going to replace that with just 1 DPS. Gotta have a, let's see if that works. No, you can't find string replace function because I need to load the string R library, which we'll do here at the top. Library string R. And then I'm going to go all the way back down here to this. Ta-da! Okay, oh no, that didn't, wait. That didn't help at all. Because I did new lines, so I got to do new lines there, I think. See if that works. There we go. So now we get a DPS there, and run that chunk. There's a DPS there, and now we can pivot longer. Awesome. So now we've pivoted, got a bunch of NAs, but I think that's okay. No, they're all NAs. That doesn't seem quite right. Oh no, there are values in there. Okay. So got pivoting longer, and we can now try to do a ggplot. AES, gonna do it the same as before, X equals DPS, Y equals CTL, and for starters, we'll say color equals epitope. And we'll make that a geom point. Oh, didn't like that. Oh, yeah, I forgot to put the parens after geom point. Nope. Should be epitope, yeah. It said epitopes instead of epitope. Okay, so that's something. The legend is taking up almost the whole figure. So that's, you know, not so exciting. But we know how to fix that. We can just get rid of the legend for now. Theme legend dot position equals none. So that's better. And of course, you know that I'm going to want to facet it. So let's do facet, wrap, epitope, and we're trying to get this, the figure B, so it should all be one column. So we'll make that n col equals 1. That's not so good. Oh yeah, so there's this issue that I sort of mentioned it before, right? There's like a whole bunch of things in here. There are a whole bunch of epitopes, but there's only one that's actually plotted here. And there are different ways to do this, but see, all of these epitopes, they end in HNVW. That's the peptide sequence. So one simple way is just to filter things that are filter only for the epitopes that have that peptide in the name. So we can do filter string. Actually, before we do that, we can just make this, let's see, sig dot height equals, let's try making it 20. Let's see if that helps any. Oh, that's not helping at all. Wait, did I say height? Just made it wider. Okay, let's get. Now I want to see what I actually have in the. Let's try it like this. Fig height equals fig dot width equals, we'll call it 4. I don't think it's going to help. Yeah, helps a little bit. Not very informative, but you can see like we have all these, like all of the things in that file are being plotted. But if we want to replicate it, we just want to do the ones that have that epitope in it. So we can do filter. We're going to use another function from string R called string detect. Epitope, and it was HNVW. Oops. I spelled it wrong. HNVW. That's a lot better. I'm going to get rid of this. Well, we'll make it figure height 8. I don't know if it really needs to be that wide, but okay. So we're pretty close to this. Let's do what I want to do next. I think I want to add the line. So we'll do geom line. Not sure I want to specify the width and height. No, I do want to specify the width and the height. Going back. So now we have the line. We have that same issue as before with the NAs, right? So we can filter those out just like we did before. Filter is NA CTL. It's looking pretty good. if I do say so myself. What else do we want to do? I gotta fix the theme. I can't stand the theme. PW. Oh, doesn't like that. Oh, because I gotta do the parens. We can like relabel the y-axis if we want. But we're kind of like most of the way there. So I guess we can relabel the y-axis. Y equals magnitude of CTL responses SFC per 10 to the 6th ppmc. Oh, and we can get rid of the color. We want to make it Edward Tufte compliant. And the one thing that we didn't do is I feel like I want to make it a little bit higher and not quite as wide, but that's like really getting picky. The one thing that we didn't do, if you look really carefully, there's the order's a little bit different between this one and this one. We could fix that, but it's going to be a big hassle, so I don't really want to do that. But it's pretty, like, I don't know that there's, like, it has the original on the top here, but I don't think there's anything special about the order of these. So I'm okay with leaving it how it is. Okay, so it is, we got like 1 minute till I'm contractually obligated to tell you to fill out the survey. Questions, anything that people are confused about? I know that was like kind of a lot. I think that, like I said, this is doing all this from scratch would probably take me half a day to a day, maybe longer. So like, I wouldn't necessarily expect anyone else here to, I mean, not that I'm like the best R coder in the universe, but I wouldn't necessarily expect anyone else to be able to like crank this out in a 2 or 3 hour period. Any questions, comments? I think if you, what I would probably do if I wanted to like kind of get practice with this, and I have this in the notes, is one, you can kind of like go through again in the unfilled out one and try and do it from scratch. And two is that you can look through the data set. There are other files in the data set, and you can find ones that are like similar in format to the ones that we did and try and do this with those. And there's, I don't know if there's, I haven't looked at actually all the files, so there might even be other yucky data formats. But I think that's a good way to get sort of some practice with loading weird data. And the one other thing that I'll mention, which I don't think I mentioned, is that you know, I think it's like, it's not uncommon for people when they have data in an Excel spreadsheet and they want to load it in R to take the Excel spreadsheet, export it as a CSV, and then load it into R. I tend to prefer using usually read Excel, occasionally open XLSX, because it does have some additional features to it. Like, for example, I believe OpenXL, just in case you want to know, I mean, OpenXLSX is like a power tool for Excel spreadsheets. So like, I think that if there's like, I think you can actually pull the formatting out. So like, for example, if they're colored cells, I think that OpenXLSX can get that out from the spreadsheet. Usually that's not what you need, but every once in a while it is. But yeah, I almost always will use, when people give me an Excel spreadsheet as data, I tend to open them directly, as opposed to trying to like save it or modify the file and into like a nicer format. I prefer to do that in R if at all possible. Sometimes it's not, but oftentimes it is. As you saw, oftentimes you can go from like some pretty messy data to a data frame. Okay, any questions? Well, I guess I can share. So I will remind you, you've heard me say this before, that if you did not sign in already, please sign in. Oh, wait, that's not right. I need the, what do I need? I think Richard, if I'm lucky, is going to be putting the, there we go, here. Oh, different sizes, great. Yeah, go ahead.
No, yeah. So if you haven't signed in, please sign in. And then for the survey, there's actually a different Qualtrics link for the final section, which I'm going to drop in the Zoom chat.
Okay, so then I shouldn't share this one, is what you're saying.
The second one, no, yeah. The first one you shouldn't share, yeah.
No, the second one's the sign-in sheet.
The second one's the sign-in sheet, yeah.
Okay, so ignore the other QR code in here. Yeah, so
people in person.
Yeah.
I'll forward you the email with the QR code.
Okay, cool. I'm waiting anxiously.
Mm-hmm. Yep. Just sent.
Oh, did I get it? Yep, I got it. Okay, wait here. Let's see. Come on. Okay, there's the QR code for today's survey. And again, I'll remind you that please take a minute to fill out the survey. It helps us know whether we might want to make changes for both next year's workshop, but also the next series, or the next two series that are going to be in January, February, and March, April. And I won't even try and guilt you into it much.
And registration for workshop series 2 will go out the first week of December. And as a reminder, we'll be going over like statistical concepts. So we'll talk more about the p-values, right, which we kind of glanced over. And we'll also talk about, some modeling. So yeah.